First speaker this afternoon is Yoshiyuki Tagawa from Tokyo University of Agriculture and Technology on stress field developments in multiphase flow, drop-in packaging, soft materials to bubble rising in the surfactant solution.
Thank you very much for a very kind introduction, and good afternoon, everybody. I'm Yoshiyuki Tagawa from Tokyo, Japan. I'm very happy to be here. I know I'm the person who comes from the far place. I played, let's say, travel many hours, but I really enjoy this conference and hope I also contribute somehow in this workshop. So I'm very interested in multiphase flow. I was working on a high-speed jet or cavitation or shock waves or viscous jet, levitating droplet, and so on. And today, related to that, we are recently interested in the flow inside our body, including some blood flow in a vessels. So, for example, if we have a kind of lobe here, then we have some, let's say, risk for the rupture for this one. And then it's very important to understand the stress, local stress acting on a fluid, as well as the wall. Both are important to be understood. So far, it is simulated for using MRI, a very expensive setup to measure the flow velocity. But we come up with detecting or discussing the stress. So directly measuring the stress in the flow or in the soft material. That's it about my talk. And then we focus on the photoelastic measurement. It is kind of the old technique, which can be shown like this. So it's a plastic spoon. And if you see the photoelasticity, so you illuminate the polarization light, then it's modified or modulated by this structure and see the residual stresses inside the spoon. So this technique is has a potential, but not applied for fluid or soft material so much. So then recently, very high-speed camera can detect the polarization light. It's commercialized. Actually, this comes from the Japanese company. I actually communicate with a manufacturer to make this camera. And then it's now partially possible for measuring the stress in a flow as well as the stress in a soft material. So this is an example. So we have the microchannel, and then it's at the beginning we don't have any flow, the stationary flow, and then we start the flow. Then the stress is actually colored by the red, which shows like the boundary layer at the wall. The stress develops at the wall, and then it eventually comes to the steady state. So the principle is actually very simple. So for example, if we have some kind of photoelastic materials like polymer, then without any flow, then the polymer distributes randomly. So it can, let's say, align in a random way. But if you apply some force in the flow, then it's kind of aligned in a certain direction. So then it has a possibility to give birefringence. That means that the reflecting index in this direction and the vertical directions, that's the difference. There is a difference, and that makes us the polarization light or modulation. So this circle shows that the reflecting index for the blue arrow direction and the green arrow direction are the same in the stationary flow, which includes randomly distributed polymers or, let's say, nanoparticles. But if we have the flow, then we have anisotropic distribution that results in a different reflective index in certain directions. And why it's related to the stress? Well, if we have this kind of alignment that's related to the principal stresses, as we all know, here we have the stress tensor, and with proper coordinate transformation, we can get the principal stress in a 3 directions. then actually the flow or the polymer inside the flow or the particles inside the flow is actually aligned along these principal stress directions, and also that's sensitive to the stress magnitude. So then from this measurement, we can detect the principal stress difference, sigma 1, sigma 2, sigma 3, and then which can be detected as a phase retardation. That is one of the modulated value of the polarization light. And the other one is a principal stress directions, which oriented to the orientation, which is actually indicated in this figure. So by using this, we have developed the method for measuring the stress in a soft material and the flow. And here in this presentation, I introduce you about the stress in soft material induced by the impacting droplets. That's we are all interested in. And the other example includes the stress in flow around the bubble or sphere. Okay, and it looks like this. So it seems like a numerical simulations, but this is an experimental measurement result. So let me start from the droplet impact problem. So here we often have the droplet impact on the hard materials, and we have the splashing, spreading, or some lubrication phenomena. And then the simulation is conducted for calculating the force inside the droplet. So here the main maximum force induced by the droplet is simply scaled by rho v squared, which is very simple dynamic pressure. And then, of course, we have more detailed theory by Jose that's explaining how the maximum force induced by the droplet can be calculated. But still, we need some more further systematic work because there is some deviation from the experiment and models. And there is another group from also Godillos group, another Godillos group from Chile. They suggest some measurement system for estimating the force in the soft material. But to have the more sensitive and more systematic study, we now use the photoelastic system. So to understand more about this, let me show you the droplet impact case. So here we have the droplet impact on a soft substrate and also the sphere impact on a soft substrate. You can see how the deformation is significantly different. And about this phenomena, Cauchy number is often used. Cauchy number is rho v squared divided by E, that is the substrate elasticity, and that scales the forces. So for the droplet case, as I indicated before, it's the maximum force is scaled as a v squared. So the maximum force is scaled with a Cauchy number power to 0. And the sphere case, it is well-known Hertz contact problem. So then we can get the scaling from this Hertzian contact theory, and we get the Cauchy number minus 2/5. So then about the stresses, we ask ourselves how the droplet rheology and the substrate elasticity affect the impact force. So then how the scaling of the forces changes and what dominates this scaling. These two questions we're going to answer by using the state-of-the-art measurement system. So this is a schematic of the experimental setup. It's very simple. We have soft material. In this case, we have the urethane gel. By the way, any gel can have a photoelastic property. So the gelatin gel can go, PDMS can also go. So then we illuminate the circularly polarized light. And due to the stress inside the gel, the polarized light is modulated, and which is detected by the high-speed polarization camera. And this detects the retardation, which corresponds to the magnitude of the stress, and the orientation, which correspond to the direction of the stress. So here's the example for the measurement. I just pushed the sphere to the soft substrate and measured by this photoelastic camera. And you can see that the stress eventually develops as I push more and more. One thing we should note is that the value we get is a two-dimensional value, which is integration of the three-dimensional stress field. So we need to do some reconstruction for the forces. So which is also called integrated photoelasticity. This method is also well established in 1950s and 60s. So we just adopt this method. I don't go into detail, but there's a, let's say, well-known protocol, and we can just follow this, and we can reproduce the three-dimensional stress field. But the new thing compared to the 1950s, 60s work is that we apply to the soft substrate. So previously it was applied to the very hard material like a glass or plastic, but in our case we use it for the soft substrate. Then this is just a validation. We do the experiment and compare with the Hertzian contact theory, and we do a good agreement. So we are confident, so we can estimate how the experimental error are. Also, I don't go into detail. It's written here, so if you are interested, you can take a look. So here's what we are most interested in. So in this experiment, we just changed the viscosity of the droplet. Because if we think that this sphere case is an infinite viscous droplet, then it doesn't deform. So we can just let's say systematically change the deformation for the droplet impactor. Okay, and these are the cases, the typical movies for the droplet impact and sphere impact. And these are the typical movies for the stress measurement. So as you could note, for the sphere case, we have the most, let's say, highest stress under the sphere. And then for the most, let's say, lowest droplet viscosity case, we have very little stresses, but it's spread rapidly, and then the stress distribution also spread rapidly. And then after doing the 3D reconstruction, we can get all components of the stress tensor. So this is a sigma ZZ component, and the other one is a sigma RZ component. So based on this measurement, we can get the stress field. And in this presentation, we just focus on the maximum force. So this is a temporal evolution of the stress. And then, so for the sphere case, we have the highest peak. And the low viscous case, we have the lowest peak and having a longer time for the stresses. And we just pick up this maximum force. Of course, we have the kind of full information in experiments, so we can do much more. But let me just focus on this maximum force. And here is the result. So typically, the Cauchy number is taken as a lateral axis, and the vertical axis shows the maximum force. Actually, this is normalized by the rho v squared. It's normalized by the dynamic pressure. So now, let's take a look for the sphere case. We have, so theory tells us that the Cauchy number minus 2/5, and actually we beautifully covers this scaling. And for the very low viscous case, then we have the Cauchy number power to 0, also indicated by the theory. So there is some, let's say, crossover of the scaling. That also tells us important things, that what dominates these scalings. So to understand more, we conducted a scaling analysis. So we know that this Fmax, tilde, that's a normalized maximum force, can be written like this. But still, we know that it's depends on the Cauchy number and Reynolds number. So then based on that, this can be, Fmax can be written as a function of Reynolds number and Cauchy number. And also we know that Hertzian contact theory indicates this Cauchy number minus 2/5. Then we take this phi number, that is f max divided by minus 2/5. And that should be written by this function. So to do this, so there is a recent method proposed for understanding this crossover scaling. So we adopt that scaling. I also don't go into detail. You can just take a look if you are interested. Then the results are actually very beautiful. So all scalings collapse in this black curve. That is the function of the Reynolds over Cauchy number squared. So this is actually based on the fitting, but we have a very clear number like this. And the exact expression is written here. But this number Z, that really dominates the crossover of the scaling. So to understand a bit more about this, the Reynolds number over Cauchy number squared, that can be decomposed with these numbers, and finally we get this one. So actually what it tells that this number is a ratio between the contact time of the droplet and the relaxation time of the substrate. And then it's also the ratio between inertial force and elastic force. So before, the Cauchy number just tells us the inertial force versus the elastic force. But actually, for understanding the crossover, we need this ratio, the contact time and the relaxation time of the substrate. So even if we have a very soft or low viscous droplets, if we have even softer substrate, like a liquid, for example, then the crossover scaling is also changed, which is also predicted by this number. Okay, so this is the short summary for the first half about the stress in a soft substrate induced by the impacting droplets. And we have, using the stress measurement system, we can nicely measure this stress scaling in a soft substrate. And even we can go further, we can understand the crossover, what dominates the crossover of the scaling. Okay, so about the next talk is about the fluid stress. So actually that's kind of the new things, because the photoelastic measurement has mainly done on a solid things. But the fluid, if we think about the fluid mechanics, we often are concerned about the flow velocity rather than the stress, because if we say that we solved the Navier-Stokes equation, that means that it's solved as for the velocity. And it works for the Newtonian fluid, because it's especially the stress tensor can be written by the velocity. But in a complex flow, like blood flow and other non-Newtonian flows, even the constitution equation is unknown. So it's very important to not only knowing the velocity, but the stress itself should be understood or measured. So in that sense, the flow field measurement in a complex flow is very important, and that's really motivates us to develop this method. So we start from the simple case. We have a rectangular long channel, and then we measure in the same setup. So we have the circular polarized light emitted to this flow, and we measure it with a photoelastic polarization camera. So by the way, this camera are special because it installs micro filters in front of the sensors, and it's kind of a super pixel. It's like a color camera. So it's 4 pixels, has different linear polarization filters, and using these 4 informations, we can get the retardation and the orientation. And because the water or other, let's say, normal liquid doesn't have any photoelastic property, we just need to put something. And here we put the cellulose nanocrystal it's already nano-size, width is 20 nanometers, and the length is 100 to 200 nanometers. Then we can get the photoelastic or the birefringence signals from that. And note that it doesn't change much for the Newtonian property of the water. Okay, and because we know the theoretical distribution of the flow velocity as well as the stresses, then we can straightforwardly calculate the stress distribution, and then we conduct the measurement for checking whether we can recover this theoretical stress field. So this is a typical measurement recordings. So we have the boundary here, and then we have the higher retardation here at the center. We don't have any retardation because we don't have any shear stress at the center. So to apply this method to fluids, one thing we need to note is that there is a stress optic law that relates the retardation to the stress. For the solid, it is well known that this works for neglecting this term. The C2 is equals 0. But for the fluid case, we shouldn't take that way. So that is also very important findings for applying this to a fluid stress measurement. So if you don't have any C2 terms, then this is a measurement result, and this is a calculated result. It clearly shows a deviation. But if we modify this, then we can recover this nicely. That's also related to the fluid mechanical, let's say, fundamental things, because if you remind the velocity gradient tensor, that tells you how the neighboring fluid particles are moving or pushing. Then it can be divided into a stress rate tensor, a strain rate tensor, and a rotation rate tensors. And mainly the force or stress relate to the strain rate tensor. But we have in the liquid, of course, we have the rotation too. For example, even in a simple shear flow, we have the rotation, right? So in that case, the retardation also affected by this rotation significantly. That's not happens to the solid case, but for fluid case, we have to significantly or seriously think about that. Then this is a result of the velocity field. We use a different aspect ratio of the channels, and here's the main result. So we have used a different aspect ratio or channels, very flat or very thin, very fat, and then all of them. So this is the experimental result, and this is the theoretical estimation using the C2 values. So then we know that what happens in a fluid. So then the result looks like this. So these are the all stress tensors, stress vectors inside the rectangular channel. And using this technique, we can measure this kind of very, let's say, gigantic vector field from the measurement. So for the last part, let me show you what happens for the flow around the sphere, which has non-slip conditions. And again, let me remind you that this is experimental result images. And with let's say, moderate Reynolds number, we have very nice, reliable numerical results. So we could compare the results of the forces around the sphere. And this that shows the comparison experiment and numerics. It's really identically matches. So even interesting thing is bubbles, because the boundary conditions changes as a function of the amount of surfactant on top of these interfaces. So here's the raw image, and this is the measurement result. And from this measurement, for example, we can estimate or detect the separation point of this flow. So here, what I show you is changing the concentration of the surfactant in a flow, and with a lower concentration, the separation is almost at the rear of the bubble. But with increasing the concentration of the surfactant, then the separation point goes up, and a very contaminated case, we have very high position to have separation. And drag force for this one is almost the same as the sphere drag force. Then we can discuss how this distribution is. That's we can get more deep insight compared to the PIV measurement because we can also dissolve the boundary layer because we have very nano particles compared to the micron-sized particle in PIV. Okay, so this is the stress around the bubbles and the spheres. Okay, let me conclude with some future perspectives. So for using this, we can go even complex flow. So for example, some stress in biological systems, like small bacteria. And there is some, for example, discussions in non-Newtonian flow, non-Newtonian liquid with this helical tail. What is the main driving force? Is it really the rear weight jetting from the coil, or is there any special anisotropy of the stress? Actually, it's an ongoing discussion. So what we could do is we can make some robots, and then so this is, you can see this robot is moving and swimming. So by the way, Reynolds number is very low because we use a very viscous liquid, and then we could use this measurement technique for estimating the stress distribution around these micro organs. So this is, by the way, ongoing work, and I'm not going in detail further. And let me just conclude my talk. So we are interested in stress field in a substrate and also the flow, and we have developed a new technique using the photoelasticity. Hope it can be useful for your research too, and I'm open for collaboration, so if you are interested, please let me know. Thank you very much for your kind attention.
So, very nice stuff.
Thank you.
Thank you. I'm just wondering, so you talked about the benefits of using this technique. Can you tell us a bit about your limitations?
Yeah, thank you very much. So for the soft substrate case, it depends, the sensitivity of the photoelasticity depends on the material. So it's Wilton gel, gelatin gel works pretty well, but the PDMS, it's a little bit less sensitive. It's basically depends on the molecular weight. It's longer chain, we have the more sensitive state. And for the liquid case, we need to put some particles. In this case, we put this rod. Actually, putting the rod is important, so an asymmetric shape. So putting the sphere doesn't work. Put the rod is important. So that's so if you don't want to put this stuff, then that's one of the limitations. And the other one, the spatial resolution, that's simply limited by the camera. So that's also another limitation.
Another question?
Yeah, but it's
Okay. Yep.
Yeah. Very interesting method. So obviously it's photoelasticity, so it relies on the elasticity of the material.
Yes.
Does it work, or can you see an extension if you have a different rheologies, like elastoviscoplastic or so?
Right, that's also a very nice question. So it's also related to the stress optic law. So in this case, we connect our photoelastic properties with the stresses every component, and that basically works. Sorry, it's going somewhere. So it can be, so the conclusion is that it can be extended to the viscoelastic things, but we need more careful validation for getting the correct C1, C2 number. It will be not constant. It will be like depends on shear rate or extensional rate. Yeah, thank you.
Could you use this technique for turbulence modeling?
Turbulence modeling. Yeah, that's also a very nice question. We have applied to turbulence to this, and we can get the photoelastic, let's say, the retardation result. So the tricky thing is that we need to reconstruct from 2D to 3D. So that was a bit troublesome. We calculated, and we need 14 cameras to reconstruct it. And this camera is like not so cheap. So getting 40 camera will be a bit tricky, but
What is the price of the camera?
yeah, it's one. It's 10 million yen. So that's 100K. Is it correct? Yeah. So 14, you can buy it.
Okay, we better finish there, and thank you again.
Thank you very much.